Current language models operate on a strict dichotomy. They are typically prompted to reason, or they are trained to act. They rarely do both simultaneously. Reason-only models, utilizing methods like chain of thought, are ungrounded black boxes. Because they cannot interact with the outside world, their logic relies entirely on the internal parametric knowledge they memorize during training. Act-only models, like those built to execute API calls, face a different limitation. They can fetch external data, but they operate with myopic execution. They lack the capacity to decompose complex goals or maintain working memory across multiple steps. In 2022, researchers introduced a paradigm called ReAct. The core mechanism is straightforward. It forces the model to interleave free-form reasoning traces with task-specific actions in a continuous loop. This approach creates a mechanism for the system to verify its logic against its environment, using incoming observations to adjust its internal trajectory in real time. This standard decision-making framework relies on a basic context-to-action mapping. The current context determines the physical action. ReAct expands this baseline space to include the entire space of language, creating an augmented action space. When the model takes an action in this language space, it generates a thought. Unlike a physical action, generating a thought doesn't trigger an external environment observation. It executes entirely internally. The mathematical purpose of this internal action is to explicitly update the system's own state. The thought synthesizes the current context and writes that synthesis back into the memory for the next step. This differs from frameworks like inner monologue, which simply feed state observations back to the model. ReAct uses language to inject common sense priors and actively decompose high-level goals into smaller steps. By treating reasoning as an internal action, the model builds a self-updating record, an internal state designed to persist even as the environment provides new feedback. To observe the mechanics of these approaches, we can look at the Hotpot QA multi-hop benchmark. The model receives a question asking what software the original Apple remote was designed to control. A reason-only trace fails immediately. The model confidently hallucinates the remote was built for the iPhone, iPad, and iPod Touch. Because the context is ungrounded, this factual error becomes the foundation for the next step, causing structural error propagation. An act-only trace hits a different wall. It can query Wikipedia, but without an internal logic map, the model loops through repetitive search queries until it hits a dead end. ReAct solves this by interleaving the two. Action 1 searches the environment, returning the term front row. This triggers thought 2. The model explicitly deduces it must now search front row to see what devices control it. The physical action grounds the model in factual reality. The reasoning acts as the logic bridge, connecting raw observation to the required action. Moving from pure data retrieval to embodied decision-making, we look at ElfWorld. This is a simulated household environment characterized by complex spatial layouts and sparse rewards. The task parameters here are specific. The agent must locate a pepper shaker, pick it up, and transfer it to a designated drawer.
ReAct utilizes sparse reasoning to decompose high-level goals into actionable subgoals. These thoughts function strictly as state trackers. The model writes, "Now I find a pepper shaker. Next, I need to put it in drawer 1. Act-only agents in this same environment quickly suffer from context loss. Without an internal thought trace tracking what they have already done, they begin hallucinating actions, like repeatedly searching inside empty sink basins. Reasoning acts as the temporal working memory. It provides the continuity required to navigate environments where rewards are sparse and steps are sequential. Exposing the internal state in natural language creates an operational byproduct, the ability to diagnose and control the agent's logic in real time. Look at this failing trace. At Act 17, the agent's reasoning trace hallucinates a second keychain, directing it to an empty drawer. Because this logic is exposed in plain text, an engineer can intervene directly in the prompt. By injecting a corrected thought prioritizing the dresser, the human manually updates the heuristic. Altering a single thought corrects the agent's physical search pattern, immediately leading to task completion. Exposing the internal state in plain text transforms black box neural execution into a steerable system. Engineers can fix execution logic without relying on expensive parameter updates or reinforcement learning. The empirical data reveals clear trade-offs between these paradigms. ReAct is highly factual,
but structurally brittle, failing if search queries return empty. Chain of thought is structurally flexible, but highly prone to hallucination. Visualizing failure modes, chain of thought suffers a 56% failure rate due to hallucination. ReAct's hallucination rate is 0%. However, ReAct's weakness is search return errors, causing 23% of its failures and derailing the model's reasoning loop. To maximize accuracy, researchers engineered a hybrid system using fallback triggers between ReAct and chain of thought self-consistency. This flowchart maps the dynamic fallback protocol. If ReAct fails to retrieve valid data within a step limit, it backs off to internal parametric knowledge. Conversely, if internal knowledge lacks consensus, the system triggers ReAct to pull from the external environment. Peak performance requires engineering a system that dynamically toggles between internal parameters and external data based on statistical confidence. Implementing this via few-shot prompting has limits. Smaller models struggle to learn both reasoning and acting simultaneously from in-context examples alone. This line graph maps parameter scale against performance. When researchers fine-tuned an 8 billion parameter model purely on ReAct trajectories, its performance surpassed the zero-shot baseline of a massive 540 billion parameter model. Teaching a model to reason and act to access information is a more generalizable skill than forcing it to memorize static facts during training. This suggests a shift in model capability. Instead of scaling parameters to store more data, we scale the model's ability to interact with external environments. The core finding of the ReAct paradigm is that reasoning and acting are not separate functions, but a single, synergistic loop for general task solving.